All right. So we are doing Riemann sums is what it's called. It's basically the same concept as what we've already done with your summation and your limit as n approaches infinity. But we are going to look at a little bit with when you have starting maybe not at 1, which can be a little bit of an issue. So if you look at the definition there, which is right there on the first page, breaking it up into intervals, and you can see the intervals could potentially be different lengths, which is not a problem when you do this method. You are still going to think about how x is changing, how your change in x is changing. And you're still going to consider how many intervals you're looking at, just like we did. But at this point, we're also going to consider where you're starting from, because we started from 0 in all the other ones. And so now we're going to say, well, what happens if we don't start at 0? That's going to affect what happens, because, it's just like any graph. If you draw a graph from 0 to 2, depending on what the graph looks like, that could be a completely different look before 0. I mean, it could be some sort of wave. It could be like a polynomial where it comes up and bounces and keeps going back and through. Like, depending on where you are, you could have all different sorts of areas going on. And so you can't just limit yourself to 0 to another point. You have to be able to do it anywhere on the graph. And so this helps you do it anywhere on the graph. So we are going to start with the definition here of Riemann sums. And it's this long definition. F is defined on a closed interval AB. Delta is the partition of AB. And then they give you these different ones. So you're going from A to B, meaning A is the lower, B is the upper. And we'll see what happens when it switches. But delta x1 is the width of each interval at that particular point. So you see xi would be at any given one. X1 would be that partition. X2 would be the next one. X3 would be the next one. So it's just telling you, you're just counting up how many divisions you have. And you're doing a summation. So you're doing a summation based on that change of x. We've already done the change of x. So the change of x, you're still going to subtract the 2. You're going to put it over how many you have. This being the top one, this being the bottom one. And so you notice that integration symbol that we've used before. And now you have numbers at the top and the bottom of the integration. Whereas before you didn't have those numbers and you did a plus c, right? And so we're moving towards definite integration is what we're doing. This is kind of the in-between section. So we did indefinite integrals where you just found a new function and you said plus c. And then we're moving to definite integrals where you're actually going to have a top and bottom cap. All right, and so this is the in-between section where we do it with intervals, and then we're going to do it with integration in the next section. This is called a definite integral. Definite means that you have end caps. Indefinite means you're looking at the integration of the whole function. Definite means I am going from one to the other. All right, and so if you have a definite integral, you're going to have a top and bottom number on that little integration notation. So if you look at this integration notation, you're not used to seeing numbers. Definite integration will now have numbers there, all right? And it says the continuity implies that you can integrate. So if it is continuous on the closed interval, then you should be able to do integration on the closed interval as well. All right, so let's look at how this works. So the first thing we're going to do is we are going to figure out what our delta x is. How is our x changing? How is our x changing? And so we're going to look at delta x. And we're going to say, well, my x is changing from my highest value, which is 1, to my lowest value, which is -2. All right? And I am going to divide that by a certain number of intervals. We'll just call it n. That should look familiar.
Just give an example.
My delta x here then would be 3 over n. Easy enough, right? Here's the thing. I'm not starting at 0. So normally I would say, well, my first partition would be at 3i over n, right? But now I'm not starting at 0. So while I am going to put that I in there, now my c value, which is what you're going to plug into your function, is no longer just going to be this 3 over n times I. You have to consider where you're starting from. You are starting from -2. So now I'm going to say -2 plus 3i over n. And that is what I'm going to plug into this thing, which isn't bad here. It's a pain when you like cube it, but that's what I'm going to plug in, all right? And so I am going to go back to my function, and I am going to take this guy, and I am going to do height. That's what happens when you plug it in. That's the y value, times width. That's my delta x, right? And then I'm going to find it using limit theory. I'm still going to use my summation. I am still going to use my limit as n approaches infinity. But now I have to consider that I'm starting from somewhere other than 0. And so I am going to plug this in. So this integral can be rewritten. Instead of writing it like this, I can say, well, this is going to be the limit. And it says delta x approaches 0, but it's actually going to be as n approaches infinity of my summation from I, 1 to n, okay. What happens when I plug it in? Well, it's 2 times x. This is going to be what I'm going to plug in for x. So 2 times -2 plus 3i over n. And then I have to multiply that whole thing by my width, 3 over n. All right? So that's what I'm going to do here, all right? Now, a couple things. I can pull out my constants here. So this is a constant, and believe it or not, that is. So I can actually pull that guy out in front and then worry about my summation stuff, okay? So I can say, well, 6 over n, he can come out here. All right, we'll still have my limit as n approaches infinity. And then I really just have to worry about this guy. If I were to do the summation of a constant, right, that's going to be the constant times the n, right? And then the summation of, I can do my 3n, and the summation of the I, which is my n plus 1 over 2.
Would you get the, oh wait, now you just caused, okay.
Now, at this point, you probably want to distribute that 6 over n through so that you can see what's going on as you do that. It may do it a different way, but I'm going to go ahead and actually put him through here. 6 over n times -2n is going to give me what? Just -12. My n's are going to cancel, right? And then this is going to be plus 6 times 3. That's going to be 18 over n squared. And then if I, have this guy here, we have n squared plus n over 2, right? You can reduce this guy here. We have -12 plus 9n squared plus 9 over n squared, right? Limit theory. Remember, I'm still doing limit. Limit as n approaches infinity of this guy. Well, the limit of a constant is just going to be a constant. And then the limit of this is the coefficients because I have squared over squared. So it's just going to be plus 9. So I'm going to get -3 here.
Wait, what's...
This says if f is continuous and non-negative on the closed interval, then the area of the region bounded by the graph f, the x-axis, and the vertical lines x equals a, and x equals b is given by this. So what they're saying is if you have a function that creates some curve between a and b, then you can use integration to calculate it. All right, and they've given you some examples. This theorem just reiterates if f is continuous and non-negative on the closed interval, then the area of the region bounded by the graph can be described like this. So what we just did is actually giving us the area. We were estimating the area. We've done the area using limit theory, and now we're using limit theory when you don't start at 0, when you can start really anywhere on the graph here. So geometric figures are easy to see how this would work. All right, if I were to take this first one, and I want it from 1 to 3, it creates a rectangle, right? This next one is a line, so it creates a trapezoid. And this next one is a semicircle. All of these I can actually calculate geometrically without calculus, but calculus shows that it works the same. And so if you were to do these integrations, you would get the areas that you would calculate if you were just doing the straight length times width, or your trapezoid, 1/2 height, base 1, base 2, pi r squared. So you would get the same exact things doing the integration as well. A couple things about this. You could do this with known figures and you'll see that it works. All right, if they used a linear, like y equals 4. Obviously, pre-calculus world, we can calculate this. This is going to be 2 times 4, right? The area of this is going to be 8. If you were to do this using your theory, you would get 8. This is a trapezoid. We know how to find a trapezoid. And so if you did this process, you would see that the rules for a trapezoid would give you the same area as using calculus to do it. I mean, obviously, if I were doing this, I would use my pre-calculus because, you know, it's just using basic formulas. If you did this is a semicircle. So 1/2 pi r squared is going to give you the same answer as if you were to use your limit theory here for this, okay? So it's just showing you that these known figures work. So then the ones that are not the normals, the ones that don't give you rectangles, that don't give you circles, that don't give you trapezoids or squares or something that you know how to do, those also work. And so they just gave you these as an example to show that even these, which would give you these figures, are going to give you the same area as it would have in the pre-cal world. All right. One thing here I do want to point out, they do define this. So if you have it from starting and ending value is the same, your answer is going to be 0. You have no area if you don't have a dimension here. So if I were to start at 1 and end at 1, my width is going to be 0 because when I subtract them, it's going to be 0 over n, and I'm multiplying by that, so it's going to multiply out to 0. All right, and so if you have a starting and ending that's the same, you don't have to even bother, you're going to get 0. If it's reversed, so let's say B is larger than A here, you can just put a negative here and do it from A to B. Those are the same, okay? So if you flip your limit, if you flip your top and bottom bounds, you can just negate, all right? And so that's going to come in handy when we start doing some integration where they do flip those. And then the other thing I want to point out is if you have a polynomial, so let's say you have 3x squared plus 2x plus 5. All you do is do them like you would a regular integration. You can plug it all in, or you can do each piece and add up the answers, whichever is easier for you. And they actually give you an example of that in just a second. But any plus or minus is the same thing as just splitting it up. So if you had a polynomial with a function and a function, you can split it up and do them individually as well. If you have a constant in front of the function, you can pull it out, just like we did with our summation. All right, you can pull that out in front. And so if you look at this, they have from 1 to 3 of negative x squared, 4x, and negative 3. You can do, if you found the pieces of it, let's say you said, well, x squared is 26 over 3. From 1 to 3 for 4x is just 4, and at negative 3 you get 2. You can add them up. So you can either find them individually. So let's say it's getting overwhelming to plug in negative 2 plus 3i over n to this whole thing, right? You can take each piece of it, and then add the next piece of it and add the next piece of it, and you're going to get the same answer as if you did it all at once. Does that make sense? Because sometimes putting in this huge, negative 2 plus 3i over n is going to be difficult, right? And so you can do it however you want. You can split it up if that makes more sense to you. So to find this, b minus a, multiply by I, starting value plus. Then I'm going to take this and I'm going to plug it into my function. So I took this whole value and plugged it in for x. So I have 3, and instead of x squared, I have that whole value squared plus 2. That's my function. All right? I have to multiply that by my delta x. So I just put him out here. I'm going to worry about him at the end. 3 over n. I don't have to put him in there because he doesn't have an I or anything to worry about. Okay? So I'm doing summation. I need to simplify this first. This is what happens when you FOIL it. So FOIL this group first. -1 times -1 is +1. -1 times that is -3in minus 3in. You get -6in. Then this times this is 9i squared over n squared. This blue right here is just what happens when you FOIL this group. I just FOILed him. 2 parentheses and I first, outer, inner, last. Okay? Then I distributed the 3 through. I also did my summation. Okay, so I did kind of skip. I brought my 3 down. 3 times 1 is 3. Summation of a constant is the constant times n. 3 times 6, that's 18 over n, and then I replaced my I with n plus 1 over 2. All right? 3 times 9, that's 27 over n squared, and I replaced my I squared with n plus 1, 2n plus 1 over 6. And then my constant here on the end, that 2, well, that's a 2n when I do my summation. All right? From here to here, I combine my 3n and my 2n, okay? That's 5n. And then I multiplied it by 3 over n, 15n over n. That's how I got him, right? Added these 2 and 3, 5n, and multiplied by this guy. So I got 15. Here, I just multiplied, all right? So I reduced this 18 and 2, so this is a 9. 3 times 9 was 27, so when you distribute this, and multiply by the 3 over n, you're going to get 27n squared plus 27n over n squared. So all I did was simplify this guy, cross-canceled my 2 and my 18, right? And then I multiplied by that 3 over n. So this guy is n squared plus n. So I get 3 times 9, 27. When you distribute it, 27n squared plus 27n over, I had 1n, 2n, I have n squared on the bottom. I did the same thing over here, okay? For this one, I actually reduced my 6 with that 3 I'm going to multiply by. That's how I did that. I canceled the 6 with the 3 that's being ready to be distributed through. So that's why that reduced to 2. When I multiply all of these guys, I get this. So then I just distributed the 27. So 27 times 2n cubed, I got this. And then from this point, I just did limit theory. Limit theory here, it's the same on top and bottom, I got 15. Limit theory here is the same on top and bottom, I got -27. Limit theory here is the same on top and bottom, I got +27. So my answer is 15.